in session number 2, the first speaker is Professor Capone, and he will give a talk on slicing management through a resource marketplace. Antonio Capone, PhD in 1998, is a full professor at Politecnico di Milano, where he's also the Dean of the School of Industrial and Information Engineering, member of the University Strategy Team PolyMe 2040, and director of the Advanced Network Technologies Laboratory, AntLab. He is associate editor with IEEE Transactions on Mobile Computing and Elsevier Computer Communications, and member of the TPC of major conferences in networking. His research interests include radio resource management and planning of wireless networks, software-defined networks, and switching architectures. On these topics, he has published more than 300 papers, and finally, he is a fellow of the IEEE. So this is a pre-recorded presentation. I will play the video now, and then you might interact with Professor Capone.
Good morning. It's a pleasure to be here with you. I wish to thank the organizers for inviting me, and in particular Filippo Malandra. So the topic of my talk is slicing, and I will introduce you a new concept, which is the resource marketplace. So let's get started. So why network slicing? Probably you are already familiar with the concept. Let me just point out a few notes here. So the idea of network slicing comes from the need to go beyond the old paradigm of one network that feeds all needs. Actually, the network cannot really fit the diversity of requirements of emerging applications and services that we are already experiencing with 5G. Therefore, we want to move, 5G decided to move from a scenario where applications adapt to the capabilities of the network to a service-based architecture where it's the network that adapts itself to offer different capabilities for specific services and applications. So exactly here that we use slicing for creating virtual networks on top of a physical infrastructure. There is, however, another reason why there is quite some interest around network slicing, and it's because a sliced network is more easily to share. We know that when you want to share something, you need to create portions, different slices. It's a good idea, right? So like with a pizza, right? If you try to share a whole pizza or a sliced pizza, well, things are different. Of course, network slicing can potentially allow an easier sharing of the infrastructure because, of course, of the virtualization mechanism, and that's pretty straightforward. Also, there is a reshaping, however, of the mobile market that can modify the value chain that over the years we know has favored the OTTs with respect to local network operators. We have also to underline that, if you look around the new regulatory trends that are emerging, particularly in Europe, but not only, well, they are pushing for sharing approaches for sure. Because the reason is that they can stimulate the entrance in the market of new players, in particular some strong players of the vertical industrial domains that can take advantage of 5G. And of course, these players have more local roots with respect to the OTTs for sure. But how can we share in the network, and how exactly can we share? Well, that's exactly what I want to show you now. So let's start with what we share. We share the resources of the access network that include the radio resources and potentially also any edge computing resource that you may make available at the edge of the network. We also share the transport network capacity. Even if this part of the network is rarely a bottleneck, it may pose some limitations, so that's also a part to share. We definitely share the services and functions in the core network, including some centralized or regional cloud resources that may be available. And finally, we can share some management services that can help in managing the slice and its connected users. So for the slice tenants, this is another important part of the virtualization scheme. In this work, we will focus mainly on the access network. So coming to the how we share, well, that's obviously more complicated and with plenty of options. So that's exactly why researchers are typically more interested in this part, because of course, when you have many options, there you can identify more creative way of solving the problem, right? So if we look at the life cycle management of slices, we can notice that there are basically three components that needs to be considered. We have the slice configuration and instantiation, which is essentially a manual process through which a new virtual network is created on top of the physical infrastructure with all the features that you may need, parameters, control services that are available. This is performed on a long time scale for sure. We may say order of days, weeks, or months. At runtime, when the slice is already in operation, we need to monitor the key performance indicators that may be used for determining if the slice is actually being served according to the constraints of the specific service level agreement. Agreement that may have been defined during the instantiation phase. So this is typically done at shorter time scale, order of seconds, minutes, or hours. And finally, at very short time scale, order of milliseconds, the network has to manage resources, and in particular, the radio resources that are managed by the scheduling algorithm. This scheme is basically independent on the specific strategy that you may want to use for arranging resources in order to guarantee the negotiated code of service. And actually, there are many possibilities, considering that also the specific quality guarantees depends on the way we want to manage the risk of having insufficient resources in case of traffic level or radio channel quality fluctuations. A relatively simple approach for allocating resources and putting the risk of these fluctuations on the slice tenants, only on the slice tenant, is that of static slicing, where resources are basically statically partitioned among tenants. The advantage here is clear. You have a perfect resource isolation, but on the other side, you may have over-provisioning of resources in order to minimize the risks. On the other side, we can use dynamic slicing, where resources are pooled and used according to needs following the variations and the channel quality changes that you may have. Here, of course, the advantage is the classical multiplexing gain, but of course, you may have risks associated to the sharing because, of course, sometimes you may have insufficient resources for serving all the slices. In our work, we have firstly analyzed the potential gain of dynamic sharing, assuming a kind of perfect control of resources and optimizing the resource allocation so as to compare the working points characterized by the same statistically equivalent quality conditions. Obviously, the exact gain depends on a number of different parameters, including the specific traffic type that you serve for each slice and the quality requirements that are associated. But in general, it can be shown that the gain is rather big. So we can exploit this gain in order to be more creative in the approaches for dynamic sharing, which is exactly what we did. So we have then proposed a radically new approach based on the concept of slicing marketplace. So we have started from the observation that for dynamic slicing, the risk must be handled in a way that can clearly identify responsibilities and associated costs. So the motivation is that of enabling dynamic resource allocation for network slices, converting high-level descriptors into current physical network requirements, and to handle variations in traffic, user behavior, or position that, of course, can influence the channel quality. So obviously, the challenge is that of the contention of the limited resources of a set of slice tenants, which of course have conflicting business interests and different technical requirements. The solution proposed is based on an automated game theoretical mechanism for resource negotiation that basically defines the resource market. In terms of time granularity, this automatic resource negotiation sits exactly between the slow process of slice instantiation and the very fast process of resource scheduling. So exactly in the middle, like it's shown in the picture and in the previous scheme. Of course, the mechanism must be distributed since the agents of slice tenants must be independent and pursuing different objectives. And also, in terms of the information they share, this must be compatible with what is reasonable to assume they can share. So our slicing market game considers a set of S of players represented by the slice tenants and a set of actions they can take, which are associated to the resources they buy. XS is the amount of resources they want to buy. Also, we have a payoff function that is the difference between revenues and costs. The game is actually an aggregative one, which is pretty common in this kind of market models. So we can show that under reasonable assumptions, the game always admits a Nash equilibrium, but not necessarily a unique equilibrium. And we can also show that the best response dynamics, the well-known algorithm, always converges to the Nash equilibrium. As for the payoff function, we have defined the revenues according to a pretty common model where we have these nonlinear functions that you can see in the picture with different parameters. These parameters can describe the economic relative value of a single user and also the service elasticity to throughput. The second component of the payoff is the cost. Here we use a rather simple function where unitary cost for resource increases with the resource demand in the network, so the load, the overall load of the traffic, and with some parameters that can describe the steepness of this function increase. In order to reach a good quality equilibrium point, we have designed a double-step smoothed best response algorithm. The algorithm has a simple trick to smooth down the trajectory followed to reach the equilibrium with respect to the traditional best response dynamics. It has also some important properties which include the compatibility with the information available to each tenant agent according to the market model that we have defined, and also its ability to reach a good quality equilibrium point regardless of the order of execution of the best response. And that's another important aspect that you need to consider if you want to have a market model that can be actually implemented. We have analyzed the quality of the resolutions provided by the algorithm with some numerical results on realistic instances. In particular, we have validated the property of providing a good quality equilibrium point regardless of the order of execution. This is something that you can appreciate in the picture on the left, where we have an example. We have run several instances with different orders, and you can see in green so the equilibrium reached by the best response dynamic, and in purple the equilibrium reached by our algorithm, which is always the same. We have also shown that the equilibrium to which it converges is almost always the most fair with respect to resource allocation. This is also something that you can see in the picture on the right now, where we have the price of anarchy, price of stability, and the price of our algorithm, considering the welfare function, which is a sum of the logs of the utility functions of different tenants. So the convergence time is within 1 second, also for a relatively high number of slices, up to 20 we have tried, and this is good enough to be implemented in a real-time system. So we have also integrated our proposed approach into a system which is used by a major vendor to test production algorithms. So it's a really, a big simulation environment with very realistic models. The system actually includes also a max scheduler that is able to efficiently accommodate quality targets for slice coming from a resource orchestration scheme like ours. And that's, on the bottom you can see the reference on this specific algorithm that we have been using. We have shown that the dynamic renegotiation algorithm adapts to the resource requirements defined by the slices, quality of service constraints, and that's something that you can see in the pictures where you have different cells with variations in terms of the channel quality, and then this convergence to results that are different according to different quality requirements of different types of network slices. In conclusion, let me mention three main messages that we want to point out in our work. So the first one is that static resource allocation may be extremely limiting the efficiency of network slicing. Second is that dynamic allocation can provide rather big advantages, but it requires managing the risk of resource scarcity somehow. And finally, a marketplace of resources can be really a suitable way of distributing this risk and pricing it according to the economic laws. And that's exactly how we believe our model can be implemented. So thank you for your attention.
Thank you very much, Professor Capone, or I might say Antonio.
Thank you, Filippo.
And thank you for the personalized acknowledgement. So we have a couple of questions that I would like to ask you. So
Sure.
The first one is regarding the current status of deployment and implementation of this technology. As we've seen before, the technology is quite ahead, and policy and the actual implementation is a little bit behind. What is, in your opinion, the missing piece? Like, what would we need? What is the next thing the next piece that needs to be deployed, or in order to have this, what you have shown, be deployed in practical systems?
Well, this is a very interesting question, Filippo, actually, and I have my own opinion on this. The technology itself is being developed by the manufacturers, right? So I can tell you that most of the major manufacturers in networking, they are working on strategies for having this dynamic sharing and for allowing a sharing that is something that the tenants, right? So can be specialized tenants in different industrial sectors, or can be general purpose tenants. They can really negotiate in real time, like you do with the stock market or with the energy market, the resources they need for running their network. This is, a typical way of sharing economic risk, and from a technical point of view, we have all the instruments, right, somehow to allow this. Of course, it's a little bit more complicated in a network because the resources are distributed, but as I have shown in the presentation, not impossible, right? The problem is, of course, that, and I can tell you that, what I have seen in some of these manufacturers is they are really preparing a kind of dashboard like the one that you use for a cloud computing system, where you can really personalize in real time the amount of resources that you want to use for your task, and also put constraints and algorithms that can negotiate dynamically, with the agent of the cloud provider, right? The resource. So exactly like that kind of scheme that we are familiar with for cloud computing can be applied for telecommunication network, for 5G networks, and somehow, we, or not only the research community, but also, the manufacturers are already working in this direction. The problem is that the operators are extremely scared of this possibility, right? So they see a big risk in their business, right? They have been controlling all the business of telecommunications. They don't want to give this to others, even if, of course, they are realizing that in order to be effective with 5G, and in particular with the type of projects that involve, specific competencies in different industrial sectors, they need to cooperate somehow with others, right? So it takes some time for accepting these, and also it's the time sufficient for us, as researchers, to a little bit work more on these algorithms and make them more effective in being implemented. But the way is robust, of course. The way is there, right? So we just have to follow the way.
And also we will need an independent agent to coordinate all this, and this must not depend on any operators.
Yes.
And that's another challenge.
Exactly. But in this regard, actually, I see that most of the regulation authorities around the world, they are already aware of this possibility. So once the technology is ready, they will jump in, and for sure they can be somehow the dependent third party that can regulate the market. We have seen that in other markets, so we will see it in telecommunication networks as well.
Great. Thank you so much for sharing your insight on this very interesting and timely problem.
Thank you for the invitation. It was a pleasure.
My pleasure. Thank you. So we can continue.